Okay, this is the third component of chapter 12, which is online controller tuning. I do believe that you already heard about this online tuning, but there are something that you are still confused. Okay, so before we go into detail or we revisit our online tuning, I decide to revisit chapter 8 that's talking about PID controller, because I do believe some of you are still confused about what is PID all about. Okay, so let's go to chapter 8 first. Okay, chapter 8 talking about PID controller. What is PID controller? Okay, PID is one type of controller that commonly used in industry. There are a lot of controller in control system, but the most common one is PID because it is simple. Okay, so this PID is about proportional, integral, and derivative mode. Okay, for proportional mode, it just reduce the error. Reduce the error. For integral, it will eliminate the error. Okay, it will eliminate the error. For derivative, it will counter back for the error that change based on time. Okay, whether the error occur in a specific time, very fast or very slow, for short time or for long time, that is the function of derivative. Okay, so because of these three modes have their own function toward, have their own effect toward the response, uh, the value of Kc that represent proportional, the value of tau I that represent integral, the value of tau d that represent a derivative is really important. Okay, it's really important to determine the best value of Kc, tau I, and tau d. The best value, the optimum value, so that we get the response, okay, the response that we want, a good response. Okay, so talking about Kc, tau I, and tau d, it is called, someone might call it a controller setting. Okay, someone might call it a controller parameter, or just the PID value. Okay, so these three things would be referred to controller setting or controller parameter or PID value. Okay, what I want to tell you that it is really important for us to decide, for us to determine what is the best value of Kc, tau I, and tau d. That's why we do a tuning. That's why we do a tuning. The purpose of tuning process is for us to determine the best value of Kc, tau I, and tau d. Okay, so in order to do a tuning, you have to understand the equation for PID. Okay, this is the equation that you should, not to say memorize, you should understand. This is really simple, that it's always should be in your mind. Okay, talking about PID equation, so this one, you can write it straight away. Okay, so this is for PID, whereby the Kc represent proportional mode, tau I represent I, integral, and tau d represent d. Okay, and this equation in S domain. Why we prefer S domain compared to the T domain? Because the T domain, as you can see here, is more complicated. There are integration, there are derivative here. It's more complicated. That's why in process control we change it to S domain to simplify. Okay, so this is the equation for PID controller that it should be, you should know about this. Okay, regardless you memorize it or you understand it, just you don't have to refer to any book. If you just really hope that you can just write it. Okay, so this is the most important and the most common form of PID. When we're going to do a tuning process, or previously we talking about direct synthesis method whereby you want to design the controller, this equation should be straight away come out from your mind. Okay, so talking about a response, as you can see in this figure, these are the response when you have different mode. Okay, without a control system or without a controller, you will get this response. Okay, this one. You will get this response whereby there is no control and it's very far away from your set point. Your set point is here. Okay, very far away from the desired value. When you introduce only proportional control, okay, proportional control only, like just like I said, it just reduce the error, but it never eliminate the error. So it reduce the error from here, very big error, to become this one. So it reduce the error. Okay, when the error is reduced, when the controller only reduce the error, there are offset whereby the difference between our desired value and the currently that we get. And for a stable response, this response will achieve a steady state there. Okay, what does it mean by steady state? Steady state from a graph, whether it is a straight line, this is called steady state, or with a sustained oscillation, it is a steady state. Okay, it depend on the process model. It depend on the closed loop transfer function. Okay, I don't want to talk about more on that. But what I want to tell you here is when you have proportional mode, there will be an offset. And in chapter 11, you already know how to calculate this offset from equation. Okay, and then when to reduce, not to reduce, to eliminate the offset, the integral mode have been introduced, whereby here we have PI. Okay, PI controller means the error is reduced, but there are still some error. Okay, the area behind the graph, under the graph is the error. Okay, there is still an error, not really eliminate, or it took some time. It took some time to eliminate the error, meaning to say the settling time is longer. Okay, for proportional mode, the settling time might be shorter, but there are offset. For the PI mode, the error is eliminated, but it have a longer settling time. When the process need to be settled fast, when the response should be, when the system need to be back to the set point as soon as possible, PI is not enough. That's why came along the derivative mode. When we have derivative mode, okay, when we have a derivative mode, the error is further reduced and the response is fastened. Okay, how do we know the response is fastened? Because from here, it can be considered a settling time already. You have to check the definition of settling time if you are not sure. Okay, so from here to here is already settled. Okay, when it's already settled, meaning to say there is the settling time. this position when the response start to achieve steady state, this is the settling time for this response. As compared to Pi, it might be here, somewhere here, the settling time. Okay. Up to this point, I really hope that you can differentiate what is the difference between proportional integral and derivative. Okay. So, to recap, proportional control, there will be an offset because proportional only reduce the error, not eliminate. But when we introduce integral, it will eliminate the error, but it took some time to get steady state. As compared to derivative mode, it will reduce the error and bring back the response back to the set point faster. The settling time is shorter. Okay, that is the function of PID. Okay, so later on we will see the effect of this value. In general, this is the response when you have P, Pi or PID. The best response came from a good controller that have optimum value of PID setting. Okay. Okay. This is the effect of KC. Okay, this is the effect of KC, whereby when KC is increased from here, from top to bottom, when KC is increased, the error is reduced, right? But it will never touch a set point because it has a offset here. Okay, and also when the KC is increased, the response getting to oscillate. Okay, so this is the effect of KC. Okay, so increasing KC, the response is less sluggish. Sluggish means slow or far from a set point. Okay, and if the KC is too large, unstable degree of oscillation, meaning to say the response is getting to oscillate, the system is getting to oscillate. Okay, and then become unstable. If KC is very high, the system become unstable. That's why we need to do a PID tuning, because we want to determine what is the best value for KC at this particular system. The value of KC are not the same for each of the system. That's why we do PID tuning because it's only applicable for specific process. Okay? For KC equal to 1 might be suitable for this process, but for another process, KC equal to 1 might be not good, might be not suitable. Okay? And intermediate value is the best value. How to determine the intermediate value? It is the tuning process. Okay? Okay, this one is the effect of tau d. When tau d is increasing, okay, when tau d is increasing, the response getting reduce the response time. Okay, the settling time is reduced. Okay, because you increase the derivative element, this derivative mode will respond faster. Okay, let's say this is almost the end of the semester. You really need to you really need to use a derivative mode so that you can learn faster. Okay, so this derivative mode is to make something faster, to fasten the process, the response. Okay, and it will reduce the reduce the oscillation when you increase the tau I. But if we have too large tau D, the measurement noise is amplified. It will disturb the system. Okay? Measurement noise is something like more oscillation, and you because you don't conduct the experimental for air pressure, there are a noise when they start to introduce derivative, but I also don't have the figure, but it's okay. Just for you to, it's enough for you to understand that if too large, of course the response will be undesired response. Dalam bahasa mudahnya, setiap benda jangan berlebih-lebihan. Okay. And then oscillatory response. Okay, so intermediate is desirable. Okay, so how to get this desirable value? Again, what we have to do, we do a tuning process. Okay, we have to tune the controller. Okay, so this is the effect when we increase the tau I. Okay, when we increase the tau I, the oscillation is reduced. Okay, the oscillation is reduced, but the response is overdamped. It takes a long time to reach a steady state or a set point. Okay, become more conservative or sluggish or overdamped. Okay, if too large, the control variable is too large, it will be a overdamped. Really took long time to come back. Okay, so by that, I really hope that you can understand what is the application of controller tuning, why we really need to do this tuning. Okay, because Kc, tau I, and tau D have their effect on the response, and we want a good response. What are the characteristics of good response? Short settling time, less overshoot, short rise time, right? And whatnot. Okay. So online tuning. In your lab number 8, the tuning been conducted using software, using simulation software. But in reality, the tuning been done at a physical machine, at a real plant. Okay? Because tuning is about trade-off between performance and robustness. Remember, performance and robustness. A good performance, what does it mean by performance? Performance is a good set point tracking, good disturbance rejection. That is a performance. Robustness, this good performance can operate, should be in a wide range. Okay, that is performance and robustness. Can you differentiate between these two? Okay, bahasa mudahnya, nak performance ni baik untuk 2 hari ataupun baik untuk 2 tahun. Yang mana nak? Okay, sesuatu benda yang robust maksudnya dia baik untuk lama. Maksudnya sampai 2 tahun dia tetap baik. Okay, contohnya kita beli sesuatu barang. Boleh pakai barang tu bagus, tapi hanya bertahan dalam masa 2 hari. Ataupun kita beli satu barang, dia boleh bertahan dalam masa 2 tahun. So, yang 2 tahun itulah dia robust. Okay? Okay, we come back. Okay. So, the controller setting, which is KC, tau I, and tau D, okay, it no need to be really precisely, very point form, no need to be until 4 decimal places, no. Okay? That doesn't mean by precisely determined. It's enough when we get the response that we want. Okay. So, the third one, okay, the third one is actually what happened in industry. Next semester you're going to do your plant design. Okay, imagine a plant or a factory that produce a chemical. There will be 300 to 1000 control loop. Okay, and you cannot calculate. Okay, you cannot using tuning relation like previously calculate. Everyone calculate every KC, every tau I, every tau D for 1000 control loop. That is not possible to do. Okay, and people don't do it. So the best way to do it is people do online tuning. That is online tuning, meaning to say tune the controller here and there. Okay, they tune the controller at that machine online. Okay, for the simulation, people always do at a simulation stage first before conducting at a real plant. Kalau tak meletup lah plant tu, kena buat on the simulation dululah. Okay, so ada banyak control loop, and for yourself you actually learn single control loop for your chapter 11. You derive until you get closed loop transfer function. It's actually for single loop, meaning to say for one variable. But in reality, it could be 100 or 1000 control loop with thousands of variable. Okay. So this is to answer because some of you asking me how to tune the controller manually. Basically, people don't tune manually each controller. It's going to take a years to tune each controller, because if you have 1000 control loop, meaning to say you have 1000 controller, and each of the controller you have the KC, tau I, and tau D, meaning to say you have 3000 value that you have to find. That is impossible. Okay, so that is why people do online tuning, do at that particular machine, at that particular plant. Okay, and diagnostic technique is actually chapter 21. Okay, it's not in your syllabus, don't worry, unless we offering you advanced process control. Last time during my study I took advanced process control. Okay, so we continue. The online tuning, basically there are two methods of online tuning. So this is the first one, which is a continuous cycling method, which is a closed loop method. Okay, this is theoretically what's going on with your lab number 8 and lab your pH and lab temperature. Okay, what you are doing in that lab is actually when a process start to reach a steady state. Okay, when the process start to reach a steady state, and then you have to set the value of tau D to 0 and tau I to the largest possible value. Okay, this is the importance of controller equation. whereby KC equal KC, okay, KC over GC is equal to KC 1 plus 1 over tau I S plus tau D S. Okay, so it is why tau D is set into 0 because we want to eliminate this term. And for the tau I, we set it to be a large possible value so that when 1 over a large value, it will approximately 0. Okay, this is why we set it to be a large value. Okay, and last time in lab number your pH and your temperature, that machine using PB. Okay, whereas for the Simulink, okay, lab number 8, it used K, only K. Okay, and then I know that some of you are confused about the calculation because of the formula a little bit different. The different only about these two. Okay, because your lab pH and temperature using PB, but for your lab 8 it's using K, and PB is equal to 100 divided by KC. Okay, so it's KC or PB is the same thing, represent a proportional mode. Okay, so these are the steps for doing online tuning. In order to do the online tuning, we have to wait until the process reach steady state. This only applicable for real plant or real machine. When we do in a simulation, we don't have to wait because we simulate only at that particular time only, not from the beginning of the process. Okay, you don't have to think too much about it. Okay, so the first one is when the process reach steady state, you have to change the value of tau I and tau D into this value because we want only the value of KC or the value of PB or the value of K, which is the proportional mode only. This is the method. The method been introduced to this continuous cycling method. Okay, only tune. The first one is tune the value of KC. Okay, so the second step is when you should start with a KC with a small value and put the controller in automatic mode. Okay, and then you have to wait until you get a sustained oscillation. The question, some of you asking me why we have to wait until sustained oscillation. It's a hard question for me to answer because this is the step. We have to follow the step. Okay, in a real detail, why it is a sustained oscillation, why not overshoot, that is really process control that I don't think that you should think too much about it. Okay, it's enough for you to understand that the response is in order to get the best value of KC, the first one is the ultimate goal is to get a sustained oscillation because that sustained oscillation will represent that the value, this is the best value of KCU, the best value of proportional. Okay, the sustained oscillation is just an indicator to show that this is the correct value. Okay, without put it any guideline, without put it as a reference, how do we know what is the value of KC? What is the best value of KC? We would never know. But these people, when they develop this method, which is a tuning, online tuning method, This is the method. You test for any value of Kc until you get a sustained oscillation. Okay, so they already designed that sustained oscillation. If you get a sustained oscillation, this is the correct value of Kcu. Or in your lab, pH is Pb star. Okay, it's the same. It's referred to the same thing. Okay, how do we know it is the best value? By looking at the response. When the response is sustained oscillation, that is the best value. Okay, so this sustained oscillation is just an indicator showing that yes, this is the correct value. Okay, without that, we cannot determine. How we know that this is the correct value? And without knowing that, how this tuning process going to end? Forever, because we never know. That's why they design it to be like that. Okay, don't think too much. It's just a step. Okay, in a simple, it's just a step to find. What is tuning? Is to find the best value of Kc, tau I, and tau D. Okay, it is a tuning. That is the mean of tuning. Tune. Okay, adjust, tune, so that the best value of Kc, tau I, and tau D will give a good response, will give a good set point change, will give a good disturbance, good disturbance rejection, and a good set point tracking. Okay, so don't overthink. Okay, so this is the formula. Okay, I believe you are already show you this formula as compared to this one. Okay, this one is from the book, and this one is from your lab module, right? Okay, so as you can see here, here is Kc or Kcu, and here you have Pb and Pb star. That's why you have here is 0.6. Here you have 1.6 because of this. Okay, how to get from this to get this? You just substitute. Okay, you just substitute. You can choose to substitute here or substitute there. Okay, the easiest way, substitute this equation into this one. You should get this 0.6 times Kcu. Okay, that is how you. That is why there are a different of formula. Okay, and also some of you asking me about this one 0.5 times Tn, or just about the same here. But for the lab number 8, why we have to divide by we have to divide more, right? We have 1 divided by this value. Again, that is because of the PID equation, which is Kc 1 plus 1 over tau I s plus tau ds. Okay, so the algorithm in Simulink is basically this one. That's why for the value of I in Simulink, just in Simulink, you have to divide with, you have to take 1 divided by this one. Okay, because of this equation, because of we have PID in a Simulink, the PID controller in a Simulink block diagram, the value of I is actually this one. Okay, hope that you can still remember. If you get confused, you can refer back to that video. I'm sorry that the sound quality and that video is really undesirable, but what can we do? And I have tried a lot of things, but it's still like that. I'm sorry for that. Okay, And because of maybe that day I making video too much, okay, so the system telling me that I should take some rest. Maybe that is the maybe that is the signal, okay, a positive signal from a audio system. Okay. Okay, so the tuning process. Okay, again, what is tuning? Tuning is a process to tune, to determine the optimum value of Kc, tau I, and tau D. Okay, Kc. Okay, tuning process is a process to determine the best value of Kc, the best value of tau I, and the best value of tau D. Okay, that is a tuning process. Okay, here is some of the response when we do tuning. Okay, so it happen to be we have to get this. Okay, we want to get this. We really want to have a sustained oscillation. Okay, this is the second method for online tuning. Okay, so our uncle here, Ziegler and Nicole, propose a second method of online tuning, but it's different from a previous one because the previous one, uh, that method is to determine the best value of Kc, tau I, and tau D. But here is for us to the process model. Okay? So step test method or process reaction curve is for us to determine the G that came from our GP and GM. Okay? So that's why it have to be in a open loop whereby it just scatter for this because you want to find this. Okay? So the experimental procedure is quite simple. When the process reach a steady state, our controller is placed in a manual mode so that we disconnect our controller. We disconnect our controller because we want to find the model. Remember last time that we derive, we want to find a G, right? Same goes here. Okay. But during our direct synthesis method, we derive from a closed loop transfer function, and then we get the G. We get GC equal to something. Okay, and this G model here, when we have a real machine, we don't have a transfer function for each of these. Okay, we don't have it, but we have a physical machine or we have a real plant. So we want to determine our process model. Okay, this is all about the our step test method here is about that. So how people do it when the step input was introduced from the response we can determine the value of k, the value of theta, and the value of tau. Okay, this is one of the example. Don't worry so much because this is not a part of your CA, but it will be important knowledge for you if later on you work in a process or you deal with a machine. Okay, okay, when a step input was introduced, this is the graph and this is the response. From the response, you can draw a tangent. When you draw a tangent, you can determine the value of k, tau I, and tau D. When you already have this process model, you can refer to table 12.1 or any table that have a tuning relation, and you can calculate the controller setting. Okay? Hope you really see the difference. Okay, but don't worry so much about this. Okay, and then this is our last part, my last topic. Actually, my last two slides about a general guideline When you have a flow rate, you should use PI. When you have a pressure, also you should have I, because in these two cases, you don't need a derivative action. You don't need a derivative mode. This derivative mode will give you a noise to the system. A noise basically when you have a response graph, okay, it should be a smooth graph, but when you have a noise, you start to see something like this. You don't want it. And but in some of the cases, the noise is amplified more. And for the temperature, you need a D element because the temperature is a very slow process. Okay. And then for the liquid level, you will just need P and you just need P, or you can use PI if you want more accurate uh, response. Exactly. But if you can tolerate with the offset, you can use. I think that's all about my topic already been covered. And thank you for keep watching. In the next video, maybe